Right, okay, so this week we're kind of moving to a slightly different area, same but different, shall we say. So because this week we're looking at regression, which is a slightly different in some ways, but in terms of the predictors that we're looking at are now continuous rather than previously where we've been looking at categorical predictors. So in this case, we're looking at continuous things. So rather than having things that are separated into groups, we're looking at things that can predictors where the values can vary continuously. So have lots of variability rather than just being in discrete groups. Apart from that, and obviously that means that actually those would be displayed differently. So they'd be looking, if you were trying to plot this kind of thing, it would look more like a scatter plot where you're looking for some kind of relationship between two different things. Yep, I shall get the check-in code in a minute. I'm just waiting for that to come up actually. Where's it got to? Oh, there we are. So there we go. So we're looking at relationships rather than kind of differences between different groups, between the averages of different groups. We're looking at relationships between a continuous response and one or more continuous predictors. And that is another type of linear model. So it's, the same kind of things as we've been looking at before. They're all linear models. But this time we're looking at ones where you've got a continuous predictor rather than a categorical one. So much of what we're going to do in terms of the coding should be familiar because it's the same kind of approach. It's just that the thing that's on the right-hand side of the squiggle when we're writing a model is a continuous variable rather than a categorical one. So that has implications for how we think about these things. So it is typically we're looking at, something it's more like a relationship, more similar to something like a correlation, which we've covered previously. So it'll look like a scatter plot, and we'll do some plotting of those data as well, which is a normal part of what you do in preparation. And the only other difference, really, I suppose, is in terms of how. Well, there's two further differences. Firstly, the assumptions are similar, so it makes similar assumptions because it's a linear model with. And those generally make fairly similar assumptions. So we've got normality of residuals and also sort of equality of variance. But because we've got a continuous variable rather than one that's in groups, then the way we assess that or the way we can look at it is slightly different. So we can't use a Levene test, for example. So that's where we have to go back to interpreting the plots rather than actually using Levene tests. So it's a more of a visual thing rather than something that giving you a number at the end of the day. And that's where it gets a bit more tricky, but hopefully it should be. We'll try and make it as clear as it can be. So we'll just, on that basis, we'll just get our studio up. Okay, there we go. So the example we've got this week is looking at cerebral blood flow measurements. So that's our response. We're looking at what measurements of the blood flow through the cerebral area and how that responds to three things. So those are that's our response. It's the actual blood flow, and then we have, well, we're going to look at initially at just one predictor, but then we'll look at several different predictors, and those are all continuous. So we'll start by just getting used to it. We'll use the car package again for slightly different things this time. So we'll just get that loaded up to start with. And then we'll read in the data. So exactly the same as we've done before. So read.csv and it's blood flow. Oops. So exactly the same process as before. So read in that data and we can have a quick look at it. So here we've got a slightly different situation to where we've looked at before. because we haven't got any categories. So here we've got all continuous variables. So we can see that if we look here, so they're all numeric variables. And we've got 4 things here. So we've got, this is our response, cerebral blood flow measurement. And then we've got 3 different things. We've got measures of 3 different hormones here. We've got T4, T3, and cortisol. So those are our 3 different things that we're going to potentially look at as predictors. And those are all continuous as well. So that's the kind of the situation where we have no categories in any of our variables. So all of our variables are continuous variables. So we'll start off just by looking at what's known as simple regression, and that's where we just look at one predictor and one response. So simple linear regression. So one predictor, continuous. So simpler, one thing we should always do before we get going is this plotting things, and this is also useful because it allows us to assess another one of the predictions, or sorry, assumptions of regression, and that's that any relationship that we see is broadly linear. So it's called linear regression, and that's because we make an assumption there is a straight line relationship between our predictor and our response. So to assess that, we should just have a look at it. So we'll start off, we'll just use one relationship, one predictor. So we'll use T4, data equals blood flow. So this is just doing a quick plot, and I'll make that bigger to start with. Just to visually assess that relationship. So here we've got a scatter plot, whereas opposed to, and that's because this one on the right hand side of the squiggle is continuous, so that will make a scatter plot, whereas if that was a categorical variable, we'd end up with a box plot. So we've got T4 is our predictor, that's on the X, and our response is on the Y, the cerebral blood flow. And we can see that there looks like there's some kind of relationship there. So that looks like this is a negative relationship. It's not massively, it's not completely, not a really, really strong relationship because there's some scatter of points. It's not all in exactly a straight line. But it looks like broadly, as you increase the T4 levels, then the cerebral blood flow goes down. It's a negative relationship. And there's a bit of scatter there, like I say, but there's, that looks like a pretty straight line. There's not any obvious curvature, not any kind of really obvious curvature. Now, you don't always see it in exactly a straight line by any means, but what you're looking for is something that is a really obvious deviation of that. So if, for example, it went down in a sort of curve like that, or it went up in a curve, rather than actually something that looks broadly a straight line, then that's where you've got to think, okay, well, I might need to do something about that, because you can't use regression on things, or linear regression on something that isn't a straight line. So that looks like that's reasonable. That's a straight line, or as close as something that we were going to get. So that means we'll carry on at this point. So we'll start off. So looks linear. So continue. So the next step is to fit the linear model. Exactly the same way as we've done this before. We'll call it B1. And it's a linear model. It's basically this. So we'll just copy and paste that. So we're saying is there some kind of significant relationship between our cerebral blood flow and the T4 levels? And both of those are found in the blood flow data set. So the difference between regression and correlation is that regression fits a straight line to the data, between the response and the predictor. And that straight line has an equation which then allows you to predict for whatever value of your predictor. So your T4 here, you could say, okay, well, if for a value of 20, what is the predicted value of your cerebral blood flow? So by fitting that line, it means you can predict the Y value from your value of X. For a correlation, you're just looking at whether there's an association or relationship, but you're not making any ability to predict it because you don't fit the straight line through it, and you're not making any assumption as to which way those two influence each other. Here it matters because cerebral blood flow is our response, T4 is our predictor. So we're saying that explicitly that this is our response. So this is the one we're interested in, why it varies, and this is the one that we're going to say predicts that. So we'll fit that model, and now we're into the assumption checking section. So that's our next thing. We've fitted a model, but can we use it? Does it fit the assumptions of the analysis? So the assumptions are the same. So equality of variance first. So here, previously we used the Levene test as well as doing it by the plots. But now we can't do that because you can only use the Levene test on categorical predictors. So we've only got the visual assessment to use. So that's why it's good to know what you're looking for here. So we plot that, the first plot, the same as we did previously. And we've got the same kind of plot as we've had before when we've done this in through ANOVA, where we've got, and what we're looking for is there any obvious change in the range of variation from left to right? Particularly commonly is that situation where we see that kind of triangle or wedge shape where we have an increasing range of variation from left to right. So small values of our response, we get, the response we get small range of variation, and at the large we would get a large value, we'd get a much more wider range of variability. So here there's not really any obvious change from left to right. The range is kind of more or less the same. It goes up and down a little bit, but there's no obvious pattern, particularly say what the one thing you're most commonly going to see is that really obvious increase from left to right, where you get that kind of triangle or wedge shape. So that looks reasonable. There's no, as I say, there's no test here, so this is where you have to start to be able to really kind of actually know how to interpret these and just to look for any obvious change from left to right. You can get a situation where you have very wide range here and a narrow range here, but it's much more common, particularly in biological data, to get the situation where we've got a very narrow range on the left and a wide range on the right, and you get that kind of increase from left to right. So that looks reasonable in this case. So we'll say that actually, that's as far as we can tell. So no obvious pattern. So that means that it looks reasonable that we've got equality of variance. So the next thing is, have we got normal residual values? Here we can still use the Shapiro test. So we'll do the plot first, just to have a look at it. So exactly the same expectation. What we're looking for is these points to sit on that line. So it's a little bit off on either end, not hugely so, but we can, in this case, we can still use the Shapiro test to check that. So we check, are the residuals significantly different from a normal distribution or not? And in this case, no, they're not. So we've got a p-value of greater than 0.05 there. And so that means that those residuals are normally distributed. So that means we can carry on and look at the outcome of the analysis. So our assumptions are met. So just make a note of that. So we can actually continue to interpret what this actually looks like. So slight difference here. So again, previously we would have done an ANOVA at this point, but for the regression, you use the summary command. So we type summary B1. And that gives us quite a bit of information down here. So it's a lot of stuff here. And we'll just go through each part of that. So some of the bits at the bottom are similar to what we get from an ANOVA. So if you look at the bottom line here, we've got an F value, 2 values of degrees of freedom, and a P value. And that's exactly the same as we get from an ANOVA table, it's just presented differently. So we've got an F, we've got 2 values, the treatment and the error degrees of freedom, and a P value. And that tells us basically, have we got an overall significant relationship between our response and our predictor. So here we've got a significant regression. So we've got, so you'd summarize that with, so F would be F72.35, DF is 1,28, and the p-value is pretty small there. So that's an overall, we've got a significant regression there. So next thing up are these 2 values of what's known as R squared. This basically tells you the proportion of the variation in your response that is explained by your predictor. So this number, and we always just look at the adjusted R squared. So this is the one that we always look at because that's the one that's still the correct one, shall we say. This tells you how much of the variation in our cerebral blood flow is explained by T4. So that can vary between 0 and 1. If it's 1, that means all the variation is explained by it. And if it's 0, it means that none is explained by it. So a value of 0.7 is quite high. So that means basically 71% of the variation in your cerebral blood flow is explained by T4. So it looks like there's a strong relationship between those two. It's not 100%. If it was 100%, then this plot, all of those points would be on exactly a straight line. So the fact there's some scatter around those points means that that relationship is not explaining everything. T4 doesn't explain everything because otherwise there would be no other variation in those points. But that's quite high. So that's a very strong relationship between T4 and our cerebral blood flow. Now the bits up here tell us more about that relationship. So the coefficients table tells us some important information about that relationship. The first thing here is telling you about how significant that variable is. Now in this case, there's only one variable, and that is highly significant, as we'd expect, because we already know that there's a strong, significant regression down here. So, but if you have more than one predictor, then this tells you whether they are actually useful in terms of explaining the variation in your response. So this one is highly significant, so that is therefore important to keep. The estimate here tells you, firstly, whether this is positive or negative tells you the direction of that relationship. Now we already know from just looking at the plot, it looks like a negative relationship, but that also confirms that. So you've got a negative value there. And that tells you basically that there is a strong negative relationship between T4 and cerebral blood flow. What that represents is essentially the slope of the line that we've fit through that. This is basically these 2 bits here are what the actual line would basically make up the information you need to fit the line through those points for that predictor relationship. This one here tells you the slope, i.e. how fast does this decrease from left to right, or increase, but in this case it's a decrease. And this one is the intercept. So that tells you that basically at a value of 0 on the T4, where would that line cross the cerebral blood flow axis? So here we've only got it between 10 and 20. So actually, if we just replot that, well, actually, it might be easy just to show. So what that means is that basically, if you took that axis back to 0, then that line would cross at about 67. So that's where that line would cross if you went back to a value of T4 of 0. So the intercept and the slope are the two things that you use to describe a straight line. So where does it start? From an x-axis, x value of 0. Where does it start on the y-axis? And how fast does it change from left to right? So basically, what's the slope of that line? And this value is basically how much change in the cerebral blood flow is there for a 1 unit change in our T4 levels. So basically, if our T4 levels went up from 10 to 11, our cerebral blood flow would go down by 0.98 here. So that tells you the sort of rate of change. That slope tells you how much with a 1 unit, so 10 to 11 or 12 to 13, how much this would decrease on average. So that's how to interpret those two values. They are telling you something about the slope and the intercept of the fitted line. Now, we could actually plot that line to show you what it looks like. So I'll just bring that back down again. Now I'll have to plot it again. So let's just get this one. So we'll bring that plot back again, which looks exactly the same, but now it's on top. And now to fit the line that this model describes, so basically these two values here, we type AB line, because the other way of describing this is that A is the intercept and B is your slope. So an AB line is basically a line where it's telling you about the slope and the intercept. And we want to use the information from that model that we fitted. So it says take those values, the intercept and the slope, from B1. And the only thing you can do is tell it what color to plot it out. So that's that line. That line is the line that we fitted through those data by fitting that regression. So the regression that we've said is a strong negative relationship between T4 and cerebral blood flow that explains 71% of the variation in cerebral blood flow. That line represents the model that we fitted there. And that line is created from these two values, basically where it crosses here and how fast it decreases. So that's basically a simple regression where we've got a single variable. What you're creating is basically a model that describes a fitted line between our x and our y, and that will allow you therefore to predict from any value of x what the value of y is. And it talks about that in the actual practical schedule there. So that's a simple regression where we're just looking at one variable against one predictor and one response. But in our original data, we had several different things. So we had T4, T3, and cortisol, 3 different things, and we're interested in potentially the effect of all of those. we know already that because we've just picked out T4, that's quite important. It explains 70% of the variation already, which is pretty high. But we want to know, well, actually, that if we measure, to get the best prediction of our cerebral blood flow, does measuring T3 and cortisol actually help us? Or can we just get away with just measuring T4? So that's what's known as multiple linear regression. So the aim here is to basically try and find the best model of predicting our data. So more than one predictor. So the process is pretty similar. So previously we just had the one variable in, so we call this B2. And it's cerebral blood flow on the left. Previously we just had T4. But we want to see if T3 and cortisol are important as well, so we put those in as well. Now this time we put them in with a plus, because we're interested in them independently. So we put all three things with a plus in between each one to say, okay, well, what's the effect of T4, what's the effect of T3, and what's the effect of cortisol? So data equals blood flow. So very similar to before, but now we've got our three variables on the right-hand side, and we want to, therefore, going to assess what's the effect of all of those. Is it worth us to get the best model of our cerebral blood flow, to predict our cerebral blood flow? Do we need to measure all of those? Oops, that's just because our plot's too small. So we've created our model there, B2, and we have to go through exactly the same process again. So we check the assumptions. So same old process. Firstly, we'll do let's make that a bit bigger so it actually works. So firstly, our plot of the equality of variances. So slightly different than the previous one. You see we've got all three things involved here down there, but there's still no really obvious pattern in there. I mean, these are quite narrow together there, but for the rest of it, it's pretty similar from left to right. There's not an obvious increase in left to right or any really strong pattern in that. It's more or less kind of similar range of variability from left to right. So again, that one looks okay. So reasonably, so no obvious pattern. So that's okay. So we plot the next one. So that's our normality of residuals plot. Those look better even than the last one. So they're quite close to the line. They're still a little bit off up here, but they're pretty close to that line. And we'll do the Shapiro test. To residuals. And again, so those are normally distributed. So normally distributed residuals. So our assumptions are met. It's all looking good. So next we go on to the summary information again. So we can carry on. Right, so this time we've got similar information. So at the bottom we've got the same stuff. F, the degrees of freedom, which has now gone up to 3. So on the first number, because that represents basically how many different predictors you've got in your model. So this number is always the same as the number of predictors in that model. Still got a significant regression, and the R squared has gone up a little bit, so it's now gone up to 74%, which is not a huge change, given that we've put 2 extra predictors in. And we've got the information about each one of those again. So T4 as we expect, it's similar, highly significant, strongly negative. T3 is not significant. So that p-value is greater than 0.05. So what that means is basically T3 doesn't help us predict the cerebral blood flow in any significant way. So it's not contributing to increasing our ability to predict that effectively. So basically, the higher this value is, the better our prediction, because we'll be able to predict it much more precisely. So T3 is not worth including because it doesn't actually help us here. It's not explaining a significant amount of variability. That's not significant, so we can just basically ignore that. Cortisol, however, is still significant. I mean, it's pretty close to 0.05, but it is less than 0.05, so does seem to be helping us a little bit. So that is explaining some useful variability. It's worth including in the model. And cortisol seems to have a relationship in the opposite direction. So it's a positive value here. So it is showing when cortisol increases, cerebral blood flow also increases. But we wouldn't stop there because this one isn't actually needed. So there's no point in including that in our model. It doesn't actually help. So T3 is not significant. So not worth including. Doesn't help us predict our response effectively. So what we do therefore is we refit the model without it. Don't need to include it. So we go through the same process again. So this is when we've got T. I want to go. That's B3, isn't it? B3 is blood flow relation to T4 and cortisol. Because those are the two things actually worth including. So we fit that without that variable that's not significant, and we'll just do a quick version of this to save me a bit of time. Oops, that should be 3. So we need to check the assumptions again. We've fitted a new model, so we still need to make sure that it's looking okay. So that's looking a little bit wobblier, but it's still not, there's not a increase from left to right, so it goes up a little bit in the middle there, but it starts to go down a bit. It's kind of, there's no obvious wedge shape in that one. So that's okay. Those are looking pretty on the straight line again. We can check. Yep, so that p-value is greater than 0.05. So that's okay. We've got normally distributed residuals. So then we then do the summary. So B3. So now our model here is including both things that are significant. So cortisol is still significant and T4 is still significant as well. So we don't need to take anything else out. If we took out either of these variables now, we'd reduce our ability, or would reduce the accuracy of our prediction of cerebral blood flow, because these are significantly explaining parts of that variation. So what we're looking for basically is to just include the things here that are significant. So if you have multiple predictors, you fit them all to start with, and then you look at them and take out one by one the least significant first. So here we had one that wasn't significant, so we took that out. But if you had more than one that was not significant, you'd start off by going back, looking at the summary like this, if there was more than one that wasn't significant, you take out the one that has the highest p-value, i.e. furthest away from 0.05, refit the model, and see if all of the variables are then significant or not. Because each time you take something out, it changes these a little bit. So it can shift things in terms of their significance. So you'd basically repeat that process until you end up with just the things that are significant. And that's where we've got to here. So T4 and cortisol are both significant. So we don't want to take those out. If we did, then our ability to predict would be compromised. So that's as far as we'd go for multiple regression. For multiple regression, where you've got more than one predictor, you start off with a model that has all of those variables in, and then you remove the ones that are not significant until you end up with a model that just retains the ones that are significant in. Because what you want, essentially, if you want to use this for prediction, you want the thing that's as simplest as possible without losing accuracy. So this way, you've only got to measure two things, T4 and cortisol, and you'd still end up with a pretty accurate prediction. So 74% of that variation is explained. If you don't have to measure T3. It's one less thing to measure. Therefore it's simpler. But if we took anything out, took out cortisol, it would reduce the accuracy of our prediction. So that's why we don't take out anything else. We just go to the point where we've just got the significant things left in that model. So we've got an R-squared value, so it's about just over 74% of the variation is explained by that model. We've still got a highly significant regression overall. So the only other thing that we have to do at this point is to check whether there's a correlation between our predictors. So at the moment, we're assuming that T4 and cortisol have a kind of independent effect on, both have an independent effect on our blood flow. But what it can often happen is that your predictors are actually kind of correlated with each other. And so you have to check that when you're doing the analysis. So, and we do this through what's known as a variance inflation factor, or VIF. So what this does is check whether our predictors are actually correlated with each other. And if they are, then we have a bit of a problem. So we'll do that here. So what we've got here, we get two values, one for each variable. And essentially, what that shows you is whether there's a correlation between our predictors. If those values were high, then it would show which ones were correlated with each other. So here, the values are quite low. So that's basically a good sign. If you have a value here, one of the values here that was, say, around about 5, then that would indicate that there was a problem, there was a correlation between those variables, and we wouldn't be able to therefore include both of them together. So if there was a correlation there, at least probably two of those values both of those values would be high, and that would indicate there's a correlation between them, and we wouldn't be able to use both of those things there to predict our response. In this case, we're okay. So there's no strong correlation between those. A value around about 5 indicates you've got a bit of a problem. Anything over 10, definitely you've got a strong correlation between your predictors. So if that's the situation, then you couldn't make a model with both of these things in if these values were high. And so what you'd do is you'd put them as individually, run a simple linear regression like we did at the beginning, and look at which one has the strongest relationship with your predictor, your response, and use that one of the two that are correlated with each other. So that's not a problem here. We don't have a problem because both of those values are low. So that's basically regression in a nutshell. Most of the code in terms of all the processes, in terms of the assumptions, all of that kind of thing, how you write it all is similar to the ANOVA. The big difference is that we use the summary information to give us basically some of the same information we get from an ANOVA, the F, the degrees of freedom, the p-value. But here the difference is because we're basically fitting a line through those points. This tells us again about that line, but it tells us the relationship between these things. So here, remembering T4 is a negative relationship, cortisol has a positive relationship, and also that relates to the changes per unit change in your cerebral blood flow in relation to a unit change in each of our predictors there. So we can't easily plot this though, because we've got two things at the same time. So you could plot it, but it would be a sort of three-dimensional plot where you'd have X, Y, and Z axes. So you can plot them individually, but the actual line that's being fitted is slightly different from the one given here because you're not putting them together. So you wouldn't try to plot the outcome of a multiple regression when you've got more than one predictor, because it's basically very difficult to do effectively. But you can still interpret those in terms of the direction of the relationship and how quickly the change occurs in your response relative to a change in each of your predictors. The only other thing to mention about regression, and that goes back to that point when we have the assumption checking. If we have a problem with either our residuals or our patterning in our plots, so when we have a pattern in one of these, then you, just as you do in ANOVA, you'd consider transformation. So if you had significantly different from normal residuals, and particularly when you have this pattern in that residuals versus fitted plot, the one where you've got that wedge shape, then you would consider transformation. And if you had that triangle, then log transformation would be one to try. Otherwise, so it's basically the same kind of thing applies to any kind of linear model. If you can't meet the assumptions, then you should be looking to see, can you find an appropriate transformation? The important thing to remember is we only ever transform, for the purposes of what we're doing in this module, we only ever transform the thing on the left. So it's only our response that we would consider transforming if we needed to. So we don't do anything with the predictors, it's always the one on the left. Our response variable that we should consider taking a log of or square rooting, etc., in terms of a transformation. So transformation applies to all of the analyses. We just introduced it as part of ANOVA, two-way ANOVA, but it works. It's equally applicable to one-way ANOVA, two-way ANOVA, and also regression. So it's just something to bear in mind whenever we have a problem with meeting those assumptions. So that's regression. I'll just stop sharing that for a second. Okay, so any questions on any of that while you're digesting that? While you're typing busily or thinking about it, then the other thing I want to mention is the fact that the second test is next week. So same kind of pattern in terms of how it's going to work. It's going to be available Monday to Friday. Data will be available from Monday morning, and the test is available to be taken all the way through that week. Much the same in terms of the way it's going to work, except for this time all of the questions are going to relate to data analysis. So there's not going to be any general questions. And as opposed to previously when you had one data set, you're going to have three different data sets to work through and prepare before you do the test. So there's going to be 12 questions. Where are we? Sorry, lost me a bit. So 12 questions as opposed to 10 last time. So there's going to be 3 data sets, 4 questions on each data set, and they're going to cover, potentially could be based on any of the analyses that we've done up until today. So it includes regression, ANOVA, one-way or two-way analysis. So there'll be 3 different data sets, and there'll be basically you have to work out what's the appropriate analysis to take, type of analysis to do, form the analysis, and answer the questions on them in exactly the same way as last time. So that will be the same Monday to Friday next week.
And remember, you've got some peer reviews to write.
Oh, yes.
Hope that's working out all right. Give me a shout if you've got any questions about that.
Okay, so no questions appear to have come in. The other thing just to remind you is that we do have an on-campus session tomorrow. So if you are looking for additional support or any questions, then do come to that. I don't have the timing off the top of my head, is it? I think it's actually in the morning for a change.
It's 11 to 1, I think.
11 to 1, there we are. So, yep, there we go. So do make use of that if you wish. We'll be there and waiting for questions or trying to help out as best we can. So any queries about anything up till now, then please do just come along and get some support. Other than that, like I say, let me just stop recording that now, will we?